Welcome to the lectures on modern digital communication techniques. So, we have been discussing quadrature amplitude modulation, and we have seen in the previous lecture how you could use a scalable constellation to change the number of bits per symbol as and when needed without much alteration to the bits constellation that we have. At this point, it is important also to note that how does this play a role, right, and this will also always be used, this will be used in some later lecture. So, we have been saying that let there be a bit sequence. I am drawing taking a random bit sequence, right. So, let there be a certain bit sequence, and we have to do some kind of digital modulation using this bit sequence. I have to send it across using digital modulation techniques. So, if we are using 2 level amplitude, then it is simple that I would choose one bit at a time, because m equals to 2 means k equals to 1. So, here this would map to, let us say, minus d, this would map to plus d, and so on and so forth. If so, this is k equals to 1 and m equals to 2, right. And if we now have m is equal to 4 and k is equal to 2, suppose we have this combination, in that case we have to choose 2 bits at a time, right. It could be pulse amplitude modulation, it could be phase shift keying, or it could be quadrature amplitude modulation. If it is pulse amplitude modulation, you have 4 levels. If it is PSK, then it is 4 constellation points in the circle. If it is QAM, you have 4 constellation points again, they could be arranged in according to your own choice. If you have m is equal to, let us say, 8, in that case k equals to 3, or in other words you choose 3 bits at a time. If m is equal to 16, your k should be equal to 4, and in that case you would choose 4 bits at a time, and so on and so forth, right. So, now and so on dot dot. Again, m equals to 16 would mean that you have 16 amplitude levels. This would mean you have 8 amplitude levels. At this point, we can take a quick look. If you are doing PAM, you would need 8 amplitude levels. So, 1, 2, 3, 4, 5, 6, 7, 8. So, your range of amplitude is this one. If you were to do, let us say, QAM, we would restrict ourselves to these few, where we have a larger amplitude swing in the I channel and you have a smaller amplitude swing in the Q channel. Overall, the peak power with respect to the average power should be smaller than the case of PAM. So, that is another justification or reason why we could go for QAM signaling. Now, if you would go for QAM signaling, you are efficiently using your signals, because you have the complex signal transmission. If it is PAM, then it is a double sideband, and you need to resort to SSB in order to single sideband transmission in order to achieve a certain spectral efficiency. If you are doing QAM, you would achieve the same spectral efficiency as you would do with a single sideband system. So, now there are 2 important aspects that we need to look at. One, where we compare that if I have a certain fixed bit rate TB that we have to use. So, if we have a certain fixed bit rate TB, in that case, if it is k equals to 1, our symbol duration should be equal to that of TB. So, this is TB, let us say, right. Now, when you are using 4 level, your symbol duration is now twice. When it is 8 level, your symbol duration is thrice. When it is 16 level, your symbol duration is 4 times, right. So, what has happened is the symbol duration has become larger compared to the earlier case, right. So, we have T is equal to k times TB. We will of course discuss a particular aspect at a later time. Roughly speaking, as of now, the bandwidth that is occupied is proportional to 1 upon t, because over this symbol duration your amplitude would remain constant if it is pulse amplitude modulation. If it is phase shift keying, your phase would remain constant. If it is QAM, the amplitude and phase together would remain constant for that particular duration, right. So, what we see is that the bandwidth required reduces to transmit the same bit rate. So, that is one way of looking at the advantage that you get in sending over higher order modulation techniques. The other way to look at the same thing would be that suppose I have a fixed T, that means we are saying that I have a fixed bandwidth. That means I have a fixed bandwidth. That means, so there are two different views that we are taking. One, I have just mentioned that we compare, I have a fixed bit stream coming into the system. When I have a fixed bit stream coming into the system, I have to choose different modulation techniques. So, as I increase the modulation order, that means I go from m equals to 2 to m equals to 4, 16 and higher orders. What I am doing is I am grouping more bits together and sending them every time I send it across the channel. So, every time means every symbol, right, every waveform that I choose, and that waveform duration will be over a longer duration of time to match the bit rate. What we have said over here is that this time or the bandwidth occupied by a signal which has a certain time duration is inversely related. Just a quick description: if my pulse is rectangular, then the bandwidth or the spectrum would be sync in nature, right. And as I increase, this is 1 by t, as I increase this, right, as I increase this, this will shrink, right, this is the f. As I increase, this is going to shrink. So, this portion is going to reduce. So, if this portion is going to reduce, the bandwidth occupied would be less, right. If the bandwidth occupied is less, that means I am choosing a lesser bandwidth as t increases. So, we can say as k increases implies t increases implies b required decreases. This is important, right. Okay. The other view is, so what is the summary? The summary that we are trying to say is that if I am choosing a higher order modulation, every time I send a waveform, I am actually sending more number of bits. For example, if I am choosing one of 8 possible levels, I am communicating 3 bits. If I am choosing 1 out of 16 possible waveforms, I am actually communicating 4 bits. So, this is the notion that should be with us. So, every time I choose a waveform, my waveform duration should be dependent or should be proportional to the number of bits. So, as this becomes longer, my bandwidth becomes smaller. So, with a smaller bandwidth I can send across. Overall, I am increasing the capacity of the system, period. The next way of looking at it is, suppose you have a particular bandwidth, right. So, that means your symbol duration is decided by the bandwidth, which is 1 upon the bandwidth. So, the symbol duration is fixed. In that symbol duration, if I send 1 bit, I am sending 1 bit per symbol. If I choose 2 bits, then I am sending 2 bits per symbol duration. So, in the so my bit rate would be k bits per t seconds, k bits per t seconds. So, in the second discussion, we are saying that if k increases for t constant implies bits per second increases. And in the first notion of discussion, we say that as you increase k, your t decreases, right. In that way, bits per second also increases. So, overall, what we could summarize and say is that by this notion of increasing the modulation order, you are packing more bits per symbol. thereby you are using your channel or system more effectively than by sending 1 bit per symbol. Now, here you can clearly distinguish the difference between an analog communication system and a digital communication system. In this particular communication system, you can, if things permit, which we will see with reasons later on, we could practically make m very large. So, as you increase your m for a fixed t, let us say, right, what you are effectively getting is better bits per second, right. So, what implies higher data rate, right. You can say more spectral efficiency. Now, as communication engineers, we should be updated with the latest requirement in terms of wireless communication systems, especially the more number of bits you can send per second for a given communication system, the better it is. Like for example, if you are given 1 megahertz of bandwidth, right, and you are choosing 1 bit per symbol duration, compared to another system which chooses, let us say, 6 bits per symbol duration. The second system is actually transmitting 6 times higher bits per second compared to the first system. So, the question that could come to our mind is, does it come for free? Now, clearly, as I increase m, going by this particular picture, what we have is, as I increase m, my constellation becomes bigger and bigger, right. So, if the constellation becomes bigger, the clear thing that we can see is we need to spend more energy if we have to keep this distance the same. This is the minimum distance between the constellation points, and I had told you, I need to discuss this in details later on, that this minimum distance between the neighboring constellation points decides the error probability. So, if we have to maintain a certain error probability and increase the spectral efficiency, that means increase m, you have to spend more energy. So, that gives us a hint that if you spend more power into the system, or if you send more energy into the system, you can achieve higher spectral efficiency. That means at the cost of higher energy, right. So, initially we were discussing about the choice of constellation. So, you can see that the choice of constellation is dependent upon another factor which we did not mention there, is the bits per second that we have over here, right. So, if you have a higher bits per second requirement, you would go for a constellation which will be more efficient in terms of spectral efficiency. And spectral efficiency is a terminology which is one of the important terms that you would encounter in a digital communication system. In contrast to an analog communication system, the analog communication system will not be able to provide you with any such benefit. Whatever signal comes, you will be modulating onto the carrier. So, the bandwidth occupied would be dictated by the bandwidth of the original signal, and you can say there is a modulation index associated along with that. Whereas, in this case, it is clearly at the control of the system designer. So, the system designer can choose what is the amount of spectral efficiency that it wants to achieve, but subject to the constraint of achieving a certain amount of error probability and the constraint of total amount of power that is available to the designer. So, this is something very critical which we should be aware of. With this, we have more or less completed our discussion on linear memoryless modulations, and we have given you some of the important tenets, some of the important ways of describing the signal, and we will be using this particular framework in all future setups. So you would so this is very important that you go through all the models and all the setups, all the notations that we have used, because the entire remaining portion of the communication will be built on the particular expressions of signals, the relationship we have got with respect to the spectral representation, the properties of narrowband noise process, which we connected to white noise, narrowband filtered white noise, its power, spectral density, and its autocorrelation, because these will be used when we are studying error probability, when we are designing receivers in the next few lectures. So, once again I iterate that this forms the basis or the foundation of what we will be doing in the next few lectures. So, although again I would like to say we have briefly covered some of the important aspects, but with this you are equipped to move forward and read up other relevant materials on these kind of communication techniques, and we would not cover anything more on memoryless modulations in this particular module. So, moving down further, if we look at the constellations that we have discussed, what we see is that even QAM is two dimensional. One is the I channel, one is the Q channel. So, any point can be projected onto these two, and going by the signal constellation or the signal model, you can see that these are the two basis functions which we had described earlier. So, any signal could be having components on the cosine and the sine, and clearly here these are the components. So, that means that we have been dealing with two dimensional signals. There is a possibility, since we have talked about vectors and signal space, there we have hinted at that point that we need to go to multidimension, and therefore, we would like to look at multidimensional signals. So, there are various ways of doing generating multidimension signals. We will look at some basic ones, and then you can expand it to some other modes. So, for example, if we have, let us say, the T1 as the total time duration that is available. So, let us say this duration, this is the t axis, this is 0, let us say this duration is T1 available for signaling. What we could do is we could break it up into smaller durations, and let us say we have n times t such durations, right. And one of the ways that we could use in selecting a waveform is that we would select, let us say, one of the intervals and send, let us say, PAM signal in that, and not send anything else in any other part of time. Another signal could be don't send anything, and then you send a PAM signal here, and so on and so forth. So, in this manner you could have n different signals that you could choose, right, and each one of the signals, as you can see over here, are orthogonal to each other. Orthogonal means if I multiply this and integrate over the period from 0 to T1, I am going to get 0, because a product of this and a product of this is going to be 0, because this is non-zero and it is 0 over here, it is non-zero, this is 0 over here. So, again the number of bits that I would require to represent this would be log base 2 of n, because there are n possible choices, and So, this should be equal to k in this case, right. So, we would do some kind of PAM signaling on each of the time slots when we have a group of time slots available. So, the signal that we could represent in this case would be of the form, let us say in this particular case would be 0 0, let us say some energy E 0 0 dot 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 up to here. Let us say this is my signal number S3, then I could have S1 represented as square root of E 0 0 and so on and so forth and so on. So, these could be my signals, where you can see this is the component of the signal on the basis vector, which is this one. That means, my basis vectors could be a 1 and a whole bunch of zeros. This is my first basis vector. My second basis vector could be this way, a very simple basis vector. Third one could be this way, and so on and so forth. So, if I project a signal and which has a component here, that means I have chosen this basis vector, which is my f1 of t, and this is, let us say, f2 of 3, f3 of t, and so on and so forth. We could do a similar thing in the frequency domain, and we say that suppose you have a bandwidth B in total, then you could split up the bandwidth into n parts, right, and you could say that each of these small sections of the frequency have a bandwidth of delta f, and then you could say B is equal to n delta f. And in a similar fashion as we have done here, you could have n different choices, because you could have one of the signals as some energy in this and 0 in all the cases. You could have another signal which could have energy there and nothing over here. You could have another signal which is having energy over there and nothing in the other frequency bands. So, that means again you have n possible choices, and you could use log base 2 of n as k. So, you could do a multidimensional signaling in time or frequency, and you could also combine the time and frequency, and you could have so if this is your time axis, if this is your frequency axis. So, if let us say you have n1 such time units, and if you have n2 such frequency units, then each of these time frequency units could be used to send a signal. So, in this case you are going to have a total of n1 n2 possible combinations, and log base 2 of n1 n2 would be the number of bits that could be represented by choosing any one of these options that are available with you. Now, one might be a bit one might have a question that how different is this from having M1 amplitude selections and M2 phase selections as we did in QAM. If you look at the signal space diagram, there we had two basis functions, the cosine and the sine, right. Here we have a different thing. Here we are saying that if you look at this time dimension, this unit of time is orthogonal to this unit of time, because it is not present over here. Similarly, this unit of frequency is orthogonal with any other space in frequency, right. So, together we have n1 n2 orthogonal functions, in this particular combination, in this particular space, and you could choose any one of them in conveying an information. So, that means you have total of n1 n2 possible options, and you would select log base 2 number of bits you will be using to convey this option. This is one way of doing it. Another more efficient way of doing this could be that if we would get back to our picture here, you could say that why not I choose one of these frequencies and I would send a PAM signal on top of it. That means not a binary PAM, but a emery PAM. So, I not only have n different options over here, but each one of them has another m different options. So, that means I have m options per frequency band and I have n different frequency bands which are orthogonal to each other, right. So, together we have m multiplied by n number of options, where there are n orthogonal space, n orthogonal frequency bands, and each frequency band can have m different signals on the same dimension, because we are doing PAM, that is cos 2 pi f c t is our basis function, only the amplitude levels are different. Whereas, if you are doing QAM, that means if I am choosing this center frequency, I would use a cos and I would use a sine. In that case, each band would have 2 dimensions, right, and we have n dimensions over here. In that case, we are going to have 2 n dimensions available for us for signaling, and in each of the dimensions you can choose a PAM modulation, which would further increase your possibilities. So, by combining these, you can go from 2 dimension to n dimensional signaling. We will look at one such n dimensional signaling in the next lecture. Thank you.